So I didn't put that much money in it. So what strike to use? Now, the closer to the money, the strike is, the more premium you get. Good. But the closer the strike is to the current spot, the more likely that option you sold is going to finish in the money. And you don't want that. So it's kind of a trade-off. So to kind of make it a little bit formal, you will ask yourself the following question. Uh, the probability of exercise you can live with. So let's say I did the secure put strategy, 26 or 27 for next week. By what probability I'm willing to live with owning those 100 shares at $27? Say 20%. Okay. Now, without going into too much detail, using the Black-Scholes model, there's a so-called drift, which is basically uh, interest rates plus zero point 0.5 sigma squared times delta t. Delta t is days to expiration divided by 252. Actually, no, 365. That's how we calculate it. And period volatility equals sigma times square root of delta t. So if days equals 8, delta t is going to be 8 over 365. Okay. Let's look at that Palantir. Just because I'm teaching you guys, I'm losing money. I could have bought this thing back at 18 cents. It's what now? Oh, it's here. I'm sorry. It's still trading at 17. Oh, 14, 18. Doesn't matter. I have till tomorrow, 3:30, to get out of it. Uh, so-called implied volatility. Again, we haven't done option pricing for you guys, but it's the uncertainty number that you have to plug in to the Black-Scholes model to get the current price. That's what implied volatility means. So let's have that at 85%. So drift is going to be 5% is the current number for interest rate plus 0.5 times 85% times 0.0219. That's the drift. In fact, I'm going to multiply so that I can get more digits. That's percent. and period sigma, '85 times square root of 0.0219. That's the percent. Even though this is not statistically very correct, just for the purpose of this exercise, we're going to assume that assumptions behind the Black-Scholes model is correct. Asset returns are normally distributed. So what is the probability that price is going to be above 27, okay? Or in this case, below 27, since we're doing a puts, okay? Well, we can calculate that. We can calculate that as norm dist in Excel. The mean is 27 plus, what is that? 0.9 standard deviation is 12.57. And I want cumulative, okay? That's how we're gonna do that in Excel. So let's find out that probability. I'm just gonna do a blank workbook. My strike is 27. Oh, I need to put the current price in there. 27.15, let's say, times 1 plus the drift, and 12.87% is the volatility. So in this case, the chances that it will finish below 27 is about 2.8%. Okay. If you want that number to be higher, uh, you should have a little bit higher strike price. For example, 27 and a half. That cannot be 12, 2.21. I mean, probability cannot be 2.21. Norm dot this, okay, 27 and a half. Oh, I'm sorry. I should have said true. Okay, that's 85%. If it's 27 and a half. I made a mistake on the first one. For Yeah, for 27, it's only close to zero. In order to get the result to be 20%, let's do this. This is the strike. And you would do goal seek. We have a better way of doing it, but for now, I'm just going to do goal seek to value 0.20 by changing this. If it was available, 27.25 is the proper strike. Unfortunately, not all strikes are available. But the way you would do this, you actually would use norm.inv. I want a 20% probability. Mean is 27 15 times 1 plus. And I rounded off the volatility. So you basically invert the standard normal distribution and you get it that way. Of course, price keeps changing. Right now it's trading at 26.85. What would be 26.85? Come here. So that means 26.98 is kind of the proper strike. I tend to fly a little bit closer to the sun. I make that number typically around 30, 35%. Part of the reason is I don't actually wait for these options to expire. I trade them. But I like getting a lot more return in the beginning. Oh, I did what I always tell you not to do. Don't hard code stuff. But in this case, strikes are so much apart. It looks like 27 is kind of the right strike to do. That's pretty much all I'm going to do for you guys today, since half the class is not here. Uh, when we come back, we're going to continue with, we're going to actually start with the CAPM model. I mean, all that stuff we did on minimum variance is actually the basis for the CAPM model. Understand the thing called beta, and we're going to look at the shortcomings of that standard CAPM model. It's technically supposed to explain all the return differentials, but it doesn't. For example, historically, small cap stocks make a lot more money than large cap stocks over long periods of time. According to CAPM, the risk of the small cap stocks should be a lot higher than the large cap stocks. Yes, they are higher, but not high enough to compensate for the difference. That means there are other things, at picture. So we will talk about what we call multi-factor asset pricing models. And those models are important because when we start doing capital budgeting, we're going to have to estimate the cost of capital for the firm. The biggest part of that is estimating the risk associated with firm stock. And that comes from those asset pricing models. If you get that right, then you invest into the proper opportunities. If you underestimate your cost of capital, you take a lot more risk than you think you are taking. All right. I will see you guys in 11 days. Do not even look at the blackboard. Have fun. I mean, I'm going to do some work, but I'm going to convert that solver thing into a template where you don't have to use any of the menus. You just enter your objective function, unknowns, your constraints. You'll be done. It's the fancier version of that solver thing. And I have 45 minutes